Today we will discuss about the transfer function of optimum filter and probability of error of matched filter and correlation receiver. So previous class we discussed about that uh, we are derived that so probability of error of optimum filter equal to 1 by 2 complementary error coefficient function of S naught 1 of t minus S naught 2 of t divided by 2 into root 2 sigma naught. So this is the derived in last class for optimum filter. So here for deriving the transfer function of optimum filter, so here we can indicate h of f is then let us assume the transfer function of optimum filter. And here let us assume for calculating the transfer function p of t, the p of t equal to s1 of t minus s2 of t. Here we can take in the difference of the two input signals, s1 of t for logic 1, s2 of t for logic 0. So these are the signals that can be represented as respectively s1 of t minus s2 of t. So this is the input signal. Why here we can take in this different signal? We can minimize the probability of error. So here at the probability of error, the output S0 1 of t minus S0 2 of t are the output voltages. Similarly here we can consider the input is S1 of t minus S2 of t. Therefore, P naught of t, that is the voltage at the output of the optimum filter, is equal to, here you can represent S naught 1 of t minus S naught 2 of t. Then the Fourier transform of that signal, the output signal, here we can indicate that P naught of f equal to, so here h of f and p of f. Okay, so here there is a filter is there, filter with the transfer function is h of f, the input is p of f, and here the output is p naught of f. This is in frequency domain. So the p naught of f is equal to this relation. H of f into p of f is the relation between input and output signals that are in frequency domain. Therefrom, by using this one here, we can find out p naught of t, inverse Fourier transform of this one equal to integration minus infinity to plus infinity. So P of F. What is P naught? Here P naught of F e to the power of J 2 pi F T df. So D. So this is the inverse Fourier transform. So then here we can substitute that value minus infinity to plus infinity. So P naught of F, that is an H of F under P of F e to the power of J 2 pi F T df. So this is a P naught of T. Then here so from this one here we can write P naught square of T equal to so mod integration minus infinity to plus infinity H of F P of F e to the power of J 2 pi F T into df mod square. Okay. Then now find out the noise power, that is nothing but sigma naught square. So this is a signal power here. Now find out the noise sigma naught square. So here you can find out this sigma naught square, that is noise power at the output of the filter here. And now generally here we can write this is here we can write this one integration minus infinity to plus infinity g n naught of f into df. So this is the formula for calculating noise power. So here what is the g n naught of f? Here the filter is there. The transfer function is h of f. The input of noise, the power spectral density of input noise G n of f is the power spectral density of input noise, and G n naught of f is output power spectral density of the noise. Then the relationship between these two are G n naught of f equal to h of transfer function whole square into Gn of f. This is one of the important relation here we can remember. So this is formula for calculating noise power, and the output power spectral density is related with input power spectral density by using this formula. So here then we can substitute so noise power, this equation into noise power sigma naught square equal to integration minus infinity to plus infinity. So h of f mod square into gn of f into df. Okay. Therefore, p naught square of t divided by sigma naught square equal to integral minus infinity to plus infinity h of f p of f and then e to the power of j 2 pi f t df mod square divided by integration minus infinity to plus infinity h of f square g n of f into df. Okay. Then, so after solving this above equation by using Schwarz inequality according to or apply Schwarz inequality and then can solve this equation, you will get p naught square of t by sigma naught square attains maximum value. This is equal to integral of mod p of f whole square divided by gn of f into df. So the integration from minus infinity to plus infinity. Then, so this attains the maximum value when the transfer function is equal to h of f is equal to. So by applying that Schwarz inequality, so then according to that one, the transfer function of that matched filter. So because why here the optimum filter is matched filter, p naught square of t by sigma naught square is attains maximum value. That filter is a matched filter. So here we can attain that maximum value. The transfer function must be equal to the k is the arbitrary constant k into p star of f, that is the complex conjugate of this power input signal p of f divided by gn of f into e to the power of minus j 2 pi f t. This is the transfer function for that matched filter to maximize that signal to noise power here. Here you can remember these two equations. So these two are very important for the matched filter. So in this matched filter, that signal power to noise power is maximum attains maximum value when the transfer function is h of f equal to k into p star of f divided by gn of f into e to the power of minus j 2 pi ft. So now, after calculating this one here, we can calculate the impulse response of the matched filter. This impulse response of impulse response of matched filter. So here we well known about that h of f of this matched filter, h of f k into p star of f divided by gn of f e to the power of minus j 2 pi ft. So impulse response of that one is nothing but inverse Fourier transform of the transfer function. This is equal to integration minus infinity to plus infinity h of f into e to the power of j 2 pi ft and t. So this is formula for calculating inverse Fourier transform. Then here we can substitute h of t, that is impulse response of matched filter equal to minus infinity to plus infinity. So p of f into can substitute h of f and this one e to the power of j 2 pi t minus small t, and gn of f is an input power spectral density of that noise that equal to eta by 2. So here you will get this one. So 2k by eta. Okay. So here this into d. Then here the final expression for h of t after solving the above equation 2k by eta, here p of t minus t. So this is the impulse response of matched filter. So here we know that what is p of t. The p of t the p of t. So p of t is nothing but p of t equal to s1 of t minus s2 of t. Therefore here h of t equal to 2k by eta p of t minus t. Here we can write this one s1 t minus t minus s2 capital T minus t. So this is an impulse response of matched filter. This is an impulse response of matched filter. Now calculate the probability of error of matched filter. The probability of error of matched filter. So for calculating the probability of error of a PE of matched filter, here we rewrite this P naught square of T by sigma naught square equal to so integral minus infinity to plus infinity mod P of f square divided by Gn of f into dl. We already discussed Gn of f is eta by 2. So here we can write this one eta by 2, that is 2 by eta integration minus infinity to plus infinity mod P of f. So here minus infinity to plus infinity mod P of f whole square df. So here according to Parseval's theorem, according to Parseval's theorem, so here we can rewrite this one. So that is integration of minus infinity to plus infinity P naught of P of f mod whole square df equal to integration minus infinity to plus infinity P of t here square into dt. This is equal to integration duration here taken, bit duration 0 to t p square of t into dt. So this is the notation here by using that Parseval's theorem. Therefore, so P naught square of t by sigma naught square. So equal to 2 by eta integration 0 to t p square of t into dt. And then, so what is p of t? P of t is s1 of t minus s2 of t. Then here you can solving this one 2 by eta integration 0 to t s1 square of t into dt plus integration 0 to t s2 square of t into dt minus 2 into integration 0 to t s1 of t and s2 of t into dt. Okay. So then here after solving this one 2 by eta s1 square of t is an power within the duration 0 to t. So that's why that indicates that that is an energy. So that's why here we can write this one is, and again here is. So actually here we can indicate that this is an E S1. Here we can indicate this is an ES2, and here due to the correlation here we can indicate that this is an ES12. So here we can take up on ES1 equal to ES2 equal to minus ES12 equal to ES. Okay. So we can taking this one here, we will get this one and plus 2 ES. Therefore, this is equal to 8 ES by eta. Okay. Then this one is substitute into probability of error. This is substitute into the probability of error equation. So what is it? PE? So PE equal to 1 by 2 complementary error coefficient function. So here S01 of t minus S02 of t whole square. Here we can S01 of t minus S02 of t divided by 2 into root 2 sigma naught is whole squared, and again that is 1 by 2. So this is equal to 1 by 2 complementary error coefficient function of this one is equal to t naught square of t divided by 8 sigma naught square whole to the power of 1 by 2. Here we can substitute that value into in this equation. So that is an here. This is equal to 8 ES by eta. So 8 ES by 8 here eta whole to the power of 1 by 2. You will get the resultant one is 1 by 2 complementary error coefficient function of ES by eta whole to the power of 1 by 2. This is a probability of error for matched filter. So this is very important. So probability of error of the matched filter is equal to equal to 1 by 2 complementary error coefficient function of ES by eta whole to the power of 1 by 2. So okay, next class we will discuss about correlation receiver. So this is a very important relation to calculating the probability of error of any modulation technique by using this formula. Okay, thank you.